Hey, good morning. Welcome to this session on JVM architecture. This is from Sversity. Sversity is a learning aid service from Koyya Enterprises. And this session is essentially a preparatory session for Sversity TechChats on JVM architecture and writing the performant code. So we'll be looking at of course, we'll start with introduction and we look at how the JVM compilers work, how the JVM memory is organized, and how the JVM takes care of garbage collection. These are the three important items that we are going to cover in the context of JVM 11. Okay. So let's start with what is a, a general understanding of Java platform, first of all, because for many people, Java means the Java programming language, which is not entirely true. Java is actually a platform which consists of various components. One of them, and the most important one of them, is JVM, or Java Virtual Machine. As you can see in its name, it's a virtual machine. That is, it's an abstract machine. The good thing about this virtual machine is that it is a cross-platform machine. In the sense, this virtual machine can be, you have support for this virtual machine on various operating systems. It runs on Linux machines, it runs on Mac machines, it runs on Windows machines. So that way, if you can run virtual machine on a given operating system, that means you are ready to develop applications for JVM. Just like how the real machines run the code that is called as machine code, here the JVM runs its own machine code called bytecode. And the way it does this job is by interacting with the underlying platform. So JVM runs the bytecode by translating it into the underlying machine code. That means if you supply bytecode to the JVM, JVM supplies the machine code to the underlying machine to get the actual job done. So that you need not to, as a developer, you need not to worry about the underlying machine. You only worry about the JVM. Right? We'll look into this point, why it is so important, in the next few minutes. Apart from JVM, the other important component is Java programming language. It's a platform independent language, we all know. It's a general purpose language in the sense it is not meant for just only one single purpose like scripting or for data science or for web development or something like that. Rather, it is meant for any kind of applications. It supports object-oriented programming paradigm from the beginning. It also supports functional programming concepts starting from Java 8. Of course, from the beginning, it supports multi-threaded programming and so on. So it is essentially a general purpose programming language. And JDK, the third important component, or in its full form, it is Java Development Kit, is a suite of tools for the developers. So if I am a developer, if I want to develop some applications to run on the JVM, I need some tools. And those tools are supplied in the form of the JDK. What do we find in these tools? Of course, the Java C compiler, all right, and the Java programming libraries. There are a lot actually. These are basic two things. So you'll be using the Java libraries like maybe Java util libraries, IO libraries, blah, blah, blah. And you write your Java program and then you use Java C compiler to compile your Java code into the bytecode. As a developer, that's what you do. And this bytecode, once you supply it to the JVM, it runs that bytecode in tandem with the underlying machine. And finally, the JRE, Java Runtime Environment. This is the one which is essential for the JVM to run. right? When we say we are running JVM and JVM runs the our bytecode, it is not just sufficient, right? Just by giving bytecode, JVM cannot do its stuff. JVM requires few other things at runtime, and all of those dependencies are provided by the Java runtime environment. So this is all these four things essentially forms the Java platform. Let's go a little deeper into these things. Okay, maybe, yeah, there is a, what do you call, a visualization here, just to understand how they are related to each other. Just look at this point. You are a developer, let's say. What do? You write a Java program by using the Java libraries of the JDK. And Java C is the one which compiles the Java program. And Java C is part of JDK. And this Java C, by compiling the Java program, what it does, it produces the bytecode. It produces the bytecode. As a user of the application, you invoke the JRE. When you run the Java command, essentially it invokes the Java runtime environment so that it provides the environment for the JVM. So JVM starts as part of it. And what this JVM does, it executes the bytecode. But JVM is an abstract machine. It is not a real machine. It requires a real machine. So it executes this bytecode, and how it is doing its job? It runs on a platform, any platform, platform means the hardware plus operating system combination. So that is how these various components of Java platform are related to each other. I hope you got an understanding. Little bit more about Java platform, essentially its background. It was originally developed at Sun Microsystems in the 90s by James Gosling. James Gosling was one of the principal person behind this Java. And later the Sun Microsystems was sold or acquired by the Oracle. And now Oracle is the owner of Java. And it has two JDKs, or it offers two JDKs. It's not that Oracle offers them. In a way, Java is available in two flavors, essentially. Not only two, but these are the most famous ones. The Oracle JDK, this is supplied by Oracle, but it is only free for development. So as long as you are developing the application, you can use Oracle JDK. But once you want to actually run this on a server machine, want to do some business with that, it is not free. You need to pay license fees to Oracle. In case, if you say like, no, I don't want to pay that license fee, then you have a open source free to use version in the name of OpenJDK. It is exactly same as Oracle JDK. There is no difference. The difference is that Oracle JDK is only free for development, but not free for usage. OpenJDK is free for both development as well as for usage. So why we need to pay license fee? What is the advantage of using Oracle JDK when we spend some money on license fee? Obviously, you'll get support, right? If there is something not working the way you are expecting, Oracle gives you support. When it comes to OpenJDK, also you get the support, but there is no guarantee because it is open source one. The Java community tries to fix bugs as quickly as possible, but it is not a bonding on them. All right. So this way you need to keep in mind. And when it comes to a bit of history, in 1996 was when the Java first version was released. And I had an opportunity to work on the first version of Java. Of course, I have been using Java since its version 1. And Java 8 was one of the breakthrough versions in the recent past. In 2014, it was released. And it is the most deployed version even today. Most of the applications across the world still run on Java 8 long-term support version. But when you're starting a new project in the last 1 decade, you may not start with Java 8 because Oracle ends support for Java 8. You will need to choose some other latest version So the Java version 11 is the most used LTS version, that is long-term support version, that people use when you start a new project in the last 1 decade. It is still the go-to version for people to start a new Java project. Even though Java version 21 is the latest LTS released in the just last year only, people, it's not that the moment you release a version, people or industry just goes and uses it. No, you need to do a lot of what do you call due diligence before you choose a version, before you migrate from one version to other version, and etc. All right. So because Java 11 is the one that you most likely use these days, we are basing the discussion on Java architecture on 11th version of Java in this session. Okay, now let's go a little bit more deeper into the Java virtual machine. As we pointed out earlier, it's an abstract computer. A computer means it has to have some hardware, basic things, right? CPU, the IO processors, ALUs, and its own instruction set, blah, blah, blah. This is an abstract computer. It is having its own instruction set, but no hardware. JVM is a computer with its own instruction set, means you can, if you have written any assembly programs, you can write assembly programs even for JVM also using its instruction set. But only thing is that that instruction set is not backed by any hardware. There is no hardware to interpret those instructions. All right. But how do you, what do you call, what these instructions, when you write a program using these instructions of the JVM, what do you call that program? That is what bytecode is. So if I do not have any other work, if I have a lot of patience, I can write a program for my JVM directly by using the instruction set of the JVM. Then I get the bytecode directly. There is nothing like I need to compile or something. But that is unnecessary tedious job, right? Nobody write assembly code directly for your Pentium chips or Mac chips or whatever. Rather, you use some high-level language. So the most prominent high-level language for writing, for getting the bytecode for JVMs is, of course, Java. But Java is not the only language, remember. You can use Kotlin, you can use Scala, you can use Groovy, you can use Clojure. There are several languages you can use to write your high-level code or your program using that high-level language, and then use an appropriate compiler to generate the bytecode instructions. When it comes to Java, it is Java C is the compiler name, right? You might have used this many times, several times. So Java C compiler takes our Java program and generates the bytecode. This bytecode, because there is no supporting hardware directly, this bytecode is further need to be translated into the machine instructions of some other real machine. The translation happens either through compilation or by interpretation. That is, these are the two different ways of doing it in this world, right? So in the case of JVM, the default way of doing it is interpretation. So the JVM have an interpreter. All it does is like it takes your bytecode and interprets them into the underlying machine code. That means as long as you have an interpreter that can translate to a target platform, your Java program that you write only once can run on any of those platforms. That's why we call Java as platform independent language. When you write the code, let's say if you are using C, if you are writing C program, what is the size of integer? It is decided by the underlying platform. It is an 8-bit machine or a 16-bit machine or 32-bit machine or 64-bit machine, depending on which the size of the integer is decided, and based on which you can decide like what is the maximum integer value that you can use in your program. That means your program is very much written for the underlying machine in C language. When it comes to Java, your machine is your JVM, not the underlying platform. Your JVM itself is having its own chipset and other things virtually. So JVM says that the integer version is 32 bits. So no matter what is the real size of the integer on the underlying machine, as a developer, when you write Java program, you always think integer means 32 bits, means this is the maximum value I can store it in as an integer. So you will get that peace of mind. You will get that peace of mind. The underlying interpreter translates this 32-bit integer to whatever that format that underlying machine is expecting, depending on whether it is 8-bit or 16-bit or 32-bit, luckily, or 64. Right? So that way, the interpreter of the JVM is the one offers you that class across platform support. But only worry with this interpreter is that it is inefficient. Every instruction it reads and converts it into the underlying machine instructions. It do not do it just only once. For example, if there is a loop, that loop is having 10 instructions. You run that loop for one iteration. In the first iteration, interpreter translates each of those 10 instructions into the underlying machine instructions. Perfect. But if you are going through the second iteration in the same loop, interpreter again translates those 10 instructions into the underlying machine instructions. This interpretation takes time and it is repeating in the loops. Let's say there is a function. That function is having some 10 lines of code. You call that function, 10 lines of all those 10 lines gets interpreted. You call the function once again those 10 lines are interpreted. Because of which the Java applications tends to be slower if it is just only the interpreter if it is working. But the good news is that JVM actually follows specifications. The specification says that this is how it should work. But the real implementation can do a lot of things to optimize this behavior. The implementation of the JVM specification by Oracle is called as a hotspot implementation, or you call that JVM as hotspot JVM, which is available as part of OpenJDK also. The hotspot JDK or hotspot JVM, it does few other things on top of basic interpretation. What is it? The first thing is that it offers you something called adaptive compiler. Hotspot JVM offers you something called adaptive compiler. What is it? It offers you a compiler. It's not actually one compiler, but just for the simplicity's sake, assume that there is a compiler that is part of the JVM. Compiler's job is to compile the Java code, but compilation takes a lot of time. If you have done any course in how the compilers work, it need to go through that code, first pass, second pass, blah, blah, blah. It has to do a lot of things, right? So it takes a lot of time. If you are doing that compilation at the development time, that is fine. You write the code for 1 month and it compiles for, let's say, 5 minutes. That is okay. But in case of JVM, what is the source code? Byte code. And if you start compiling the byte code after you start running the application, and if it takes 5 minutes to do that job, then what that user feel? Let's say I want to do some work. I want to open a spreadsheet written in Java, and it takes five minutes to just to appear on the screen because the Java compiler is trying to compile your byte code into the machine code at runtime. Absolutely not acceptable. The problem here is that if you are compiling the code at development time, it becomes machine specific. We don't want that. If you want to be machine independent, you need to do this compilation at runtime. But it takes a lot of time, which is again not acceptable. So we need to find a compromise. We need to find a middle ground. That's what this hotspot implementation does. What it does is that it allows the interpretation to take place. So as long as your application is running, the interpretation always works. But the compiler sits in a corner and keeps observing how this interpretation is happening. As long as this interpretation is very linear, like you have 100 lines of code, first line, second line, third line, that way it is just executing one line after one other. Compiler has nothing to do with it. But the moment the interpreter enters into a loop, and that loop is running for, let's say, 1,000 times or 10,000 times, then compiler feels that, oh, interpreting the same code for 10,000 times is bad. Let me jump in. Let me jump in. This loop is a hotspot. This is a performance bottleneck. So it's immediately identifies that loop as a critical portion. Why? It do not find every loop as a critical portion. Please remember, only if the interpreter is running a loop for a good number of times, not just for 10 times or 100 times, but if it is running for 1,000 times, then definitely optimizing that particular loop or compiling that particular loop gives you a lot of dividends. Then the compiler comes into picture. At that point of time, the compiler comes into picture and compiles only that critical portion of the code. Only then it compiles that critical portion of the code. Because the compiler is at runtime is observing what is going on with the interpretation at runtime and identifying the hotspots and compiling only those critical sections, we call such a compiler is as adaptive compiler. It adapts itself to the needs of the application. But keep on compiling code. Again, as I said, compilation takes a little bit more time, headroom actually. So you should not compile each and everything. It compiles only very, very critical portions which are getting executed several times. Let's say a function, there is a function, and that function is being called thousands of times in your application. Then that function only gets compiled. It keeps it in the underlying machine. Once you compile, that code has to be loaded into the underlying machine, right? But that machine may not be having a lot of memory just to keep. JVM gets only X amount of memory from the underlying machine. It need to keep this compiled code in that memory. If it is keep on compiling the code, you may end up using that memory. So sometimes what happens when it finds that, okay, I compiled this code of a particular function because it was being used several times 5 minutes ago. But now this function is not being used at all. The application behavior is that it is not using this function. Some other function it is using. If that is the case, why I want to keep that old code of the compiled code of the old function still in the underlying machine? It may remove it. That thing is called as decompilation. Right? So now you need to, you just need to visualize that interpreter is executing one line at a time all the time. But if the interpreter is found to be executing few lines of code several times, instead of doing interpretation for those few lines of code, which is identified as a hotspot, the compiler gets into the job and compiles that piece of the code. And that way, the JVM speeds up its performance. All right. So this variety of optimization, all right, this way of optimization makes Java programs as good as any other programs. As good as any other programs. Right. So this is very important. This is very important. And then, of course, hotspot implementations have the memory management to allocate memory as quickly as possible, deallocate or reclaim the memory as quickly as possible using its garbage collection. And we have the built-in support for thread synchronization in these hotspot JVMs. Now, let us look at how all these things actually do take place. So for that, let's look at this architecture once. JVM is consisting of three important components: class loaders, the memory or data area, people also call, and the engine, execution engine. Class loaders are the one of the important components. Then you have the memory, data area, and the execution engine. JVM, as I said, it is like any other computer. Every computer have its own process management, device management, IO management, memory management, and whatnot. Since JVM is a virtual machine, do not have the hardware, it only takes care of memory management and process management, not the device management and other things. That is all have to be done by the real hardware. The interesting add-on for the JVM is the class loader. An interesting add-on is the class loader. So let's look at each of those things one by one. Now let us look at the class loading system. Class loaders by its name is a system, a subsystem which basically loads the classes at runtime, Java is an object-oriented system, means whatever you write is in the form of classes, right? So those classes needs to be loaded first. This is one of the important thing that any JVM has to do. So the class loaders are the ones which take up that job. All right. So there are three varieties of class loaders in any JVM. They are called as bootstrap class loader, platform class loader, system class loader, or application class loader. When I say any JVM, I mean whether it is hotspot JVM or any other implementation of the JVM specification, let's say by IBM or Azure or whatever. In the previous versions, the platform class loader was in its name, in its place, there used to be something called extension class loader and etc. But in Java 11, they are called as bootstrap class loader, platform class loader, and the system or application class loader. What is their job? The job of the bootstrap class loader is to load all the runtime classes of Java. That is rt.jar. If you look at the JDK or JRE, you have a folder called you have a file called rt.jar under JRE. That is the one which contains all the core classes of Java, all your strings and blah, blah, blah. They're all part of that rt.jar. IO classes, util classes, all of them. They're all loaded as and when required. Those classes are required. As and when those classes are required from rt.jar, they are loaded by the bootstrap class loader. This is the parent class loader for any other class loader, and it is written in native code. Bootstrap class loader is something which is written in native code, means the JVM of Linux will have its own implementation of bootstrap class loader. JVM of Mac machine will have its own version or its own implementation of bootstrap class loader. So these two JVMs, that's why they cannot run interchangeably on different machines. If you download JVM for Mac, it runs only on Mac. It cannot run on Windows because the bootstrap class loader is very much platform specific. Then platform class loader, anything that is, let's say, database related platforms and blah, 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 such kind of classes are loaded by the platform class loader. And the Java classes that you and me write in the form of bytecode, the .class files, they are all loaded from the class path by something called system class loader. So classes from rt.jar are loaded by the bootstrap class loader. Classes from our own class path, application class path, are loaded by the system class loader. Anything that is specific to the given platform are loaded by the platform class loader. And these class loaders follow a thing called delegation model. In the sense, anytime in your program, let's say somewhere you have written system.out.println. System is a class. It needs to be loaded. So who is the one who does that job first? Because that is written in your program. It is the application class loader which knows that, oh, we need to load the system here, which is having that out.println stuff. But it does not do that job immediately. It will delegate that job to its parent, that is platform class loader, to the platform class loader. That guy delegates the job blindly to the bootstrap class loader. So it is always application class loader which tries to load the stuff first, but it do not really attempt to load anything. It will delegate the job to the parent. Parent immediately delegates it to the bootstrap. And then bootstrap class loader sees if the given class is part of the rt.jar. If it is, then Bootstrap class loader really loads that class. If it is not part of the rt.jar, then it will tell the platform class loader saying that, sorry, I don't find this class in rt.jar. You find it in the platform specific folders. So platform class loader try to load that class from that specific folders, whatever folders they are. If it is found, fine. Otherwise, it will tell the application class loader that, sorry, we couldn't find the class. You figure it out from the class path of the particular program. You typically give -cp or -class path, or you may set it through environmental variables, right? So application class loader goes through all the folders of the class path and figures out one by one, like where this class is found. Once it finds that class, it loads it. If it do not find the class, that's where you see the class not found exception. Who is throwing that exception? The class loaders. But the job of the class loading is not ended just by loading the class. Loading the class means you have written some bytecode in the file. That bytecode need to be loaded into the virtual memory or the memory of the virtual machine. That is the job of the initial class loading. But after loading this class, you need to look at the linking and initialization phases also. As part of linking, the class loader system verifies whether the loaded bytecode is compatible with the underlying JVM or not. Let's say you have written some you have some class code which was compiled by using Java 8 compiler, but you are using Java 11 JVM. Are they compatible or not? If they are compatible, fine. If they are not compatible, again, it will throw an exception. And once it finds that it is compatible, what that linker does is it allocates memory and initializes the statics of the class. Every class will have some static attributes. Not every class, but classes may have some static attributes. Apart from the instance attributes and locals and blah, 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 right? For static attributes, it allocates memory and initializes them with the default values. And if there are any direct references to other classes and etc., they are also loaded, and that's how the resolution happens. This is linking. Means all the required classes for the given application are loaded, and the statics are initialized with the default values. And then comes the real initializer, and it overwrites the default values with the actual values as per your program is concerned. And with that, the class is loaded. That's why you may read somewhere that when you load a Java class, the static blocks are executed automatically without you initializing the constructor. Why? Because the class loader is doing all this job in the beginning. So this is the first part of the JVM. Now comes to the second part, that is memory part, or this is also called as runtime data area. This is having, you see, there is something called method area, heap area, several stacks, several program counters, and a native system. Let us look at each one of them. What is this method area? Method area is the one which stores the code of the fields and code of your methods. Right? So in the method area, whatever class you load, that class is having some instance fields. Class is having some methods, means functions, in which you have a lot of code. All that code, including the code of the constructors, is entirely stored in the method area. This is common for the entire JVM. Means when you are running the Java application, irrespective of the number of threads you have, all the classes and the methods of all the classes are stored in the method area. But there is only a certain amount of memory allocated for that. If your application is having classes and classes and classes with methods and methods and methods, then what happens when you load a class, all of its methods need to be stored in this method area. If the class is having 100 methods, all the 100 methods are stored here. Even though you may be using only one method in your application, but still all the 100 methods are stored here. which may occupy a lot of memory, and it may actually result in out of memory error if it is too much. So that's why you should not write one Java class with hundreds and hundreds and hundreds of lines of code and number of methods in them. Keep that in mind. And then comes the heap. Heap is the second important area. In fact, this is where you'll have a lot of memory allocated for. This is also common for all the threads of the given JVM. Means for your application, irrespective of the number of threads, you have only one heap in the runtime data area. And this is where the instances of the classes, means the objects are stored. Objects and the arrays of objects are stored in the heap. Individual objects are arrays of objects. If you are keep on creating objects but not reclaiming them, then also out of memory error may happen. Right? Method area is having certain amount of memory allocated. Heap is also allocated some certain amount of memory. If you are not writing the applications appropriately, any of these memories may used up quickly and you run into out of memory error. Then you have something called machine stack, right? Machine stack is, you can see there are many. In the sense, for each thread, there will be a machine stack allocated. Certain amount of memory, not too much of memory, of course. Each JVM thread will have its own stack. What is a stack? It contains stack frames, you all know. And each stack frame holds the local variables of the current function that is executing and the partial results of any expressions that you are executing. They're all part of the stacks. If you know operating systems, how their real operating systems work, same thing here. Right? For each of the thread, you'll have a stack. For each of the method call, you'll have a frame. As long as that method is under execution, that frame is there. Once the method is completed, the frame is popped out from the stack. That's why the local variables lose their values. That you know, right? How the local variables work in Java and etc. Even here also, only certain amount of memory is allocated for a given stack of a given thread. If you are calling function after function without coming out of those functions, essentially the recursions and other things, it may so happen that the amount of memory that is allocated for the given stack might have been used up. In such case, you will get stack overflow error or exception. All right, so that is also very important. And if you are having too many number of threads, then too many number of memory machine stacks are allocated, then you may get into out of memory error. So anything too much is bad, remember. And then program counters, if you know how the real computer architecture works, you have this thing called program counter, which essentially holds the instruction or address of the current instruction under execution. So each thread will be executing some instruction, right? So for each thread, there is a program counter in which the current instruction of the thread under execution is stored. So that when the thread loses its time slot, it will be waiting for the next time slot, right? Once it gets the next time slot, the thread knows which instruction it needs to execute because the program counter is holding that value. All right, so those program counters are also very much thread specific. They're also very much thread specific. And then Java has its own JNI, right? Java native interface to work with the underlying native platforms and other things. That is also part of that runtime data area. We are not focusing on that. Okay, so this is runtime data area. Now let us look at the execution engine. Execution engine is the one which actually does the job at runtime. This is where you have the interpreter and the compilers and garbage collectors reside. All right, you can see interpreters, that is JIT, just-in-time compilers, and garbage collectors, and of course native method system. Again, that is out of focus for our discussion. So maybe it may look a little repetitive, but maybe explanatory here. An interpreter is the one which interprets the bytecode that you supply into the underlying machine instructions, because of which it offers you platform independence that we talked about already. And because you don't do any compilation or anything, it can quickly start your application and you see that application starts running, which is good. But it is inefficient when it comes to executing the loops and repeated method calls, because it will keep on blindly interpreting the same code again and again and again, which slows down, which unnecessarily or which can be optimized further. It is not that it is slowing down further, but you have an opportunity to optimize those kind of hotspots. That is where you have this just-in-time compiler, JIT compiler. In fact, Java used to have two varieties of compilers earlier, C1 compiler and C2 compiler, or they were called client compilers and server compilers. The level of optimization that you do in a client is different from the level of optimization you do on a server. See, on a client machine means some application is running on my workstation. I may do something with that application, because of which it may run some loops and blah blah blah. So it is compiled. But if it is a server machine, there is a piece of code. That code may be executed because of a request it received from a client. And how many clients are there? Maybe each client is executing that function maybe only once. But if there are millions of clients, that single function is executed by million times because of million clients. So the level of optimization that is required to be done on the server is quite different. So that's why you used to have two flavors of compilers earlier. But now it is no longer. Both C1 and C2 compilers are now integrated, and that is one now we call it as adaptive compilers. Adaptive compilers. So C1 compiler does some quick optimization, nothing much beyond that. Whereas server compiler, it actually kept on compiling the code throughout its runtime. If the server is running for 1 year, throughout that 1 year, compiler keeps profiling the code, keeps identifying the hotspots, keeps compiling them, and keeps compiling them again and again and again, as and when they are required, of course. All right, so that's what it is. Identifies the hotspots and compiles them into a portion called code cache. Again, with limited memory. It decompiles when that piece of code is no longer be executed that often. And when we say compilation, it is not just direct, it's not only the classic compilation. It may do some inlining also. Let's say you typically write getters and setters, right? Those getters and setters, if you just only generate using your IDE, you are not overriding anything in them, then they are as good as public accessors. So if these getters and setters are being called quite often, the compiler may feel that it should be inlined. So they remove getters and setters from the bytecode, gives the direct access to the public attributes, as if like they are public attributes. Sometimes your code may have synchronization written, but it is being run in a single threaded application. Then also JIT compiler feels like, anyway, this application is running as a single thread, even though you do have synchronization blocks here. In such a case, it may skip that synchronization altogether. So there are several ways this JIT compiler essentially optimizes the performance of your application. That's why Java applications may look a little slower initially, but if you keep on using the application, some portions of the application, some some workflows, they get optimized, and over a period of time, they work very quickly, very fast compared to the initial times. Okay. And then comes the garbage collector, where we'll be spending good amount of time just now in a while. And its job is to reclaim the memory once it is used up. All right. So now let us look at this piece. You know, all the objects that are allocated space in the heap, and that heap is common for all the threads in the JVM. So every time you create a new instance, new string, let's say, that string instance is created in the heap memory of the JVM. Let's say if the string is part of a method, means a function, and that function is executed, that means the stack is removed, means that string is no longer being used, means the object is dereferenced. The garbage collector looks for such kind of dereferenced objects and deallocate memory so that it can allocate memory for the new objects. This job is called as garbage collection. Garbage is like essentially the objects that are no longer being used. That is all garbage. Garbage collector frees up that memory. When it is doing this job, it need to stop the entire application. It says like, okay, please stop. I am cleaning this room, and then it does that garbage collection. We call that event as stop the world event. Entire application stands still. This is the basic process. This is the basic process. Let's visualize that. Let's say this is the heap memory that is given for the given JVM. Now a new object is created. You created a string, let's say, and that is created. Every time you create any new object, they all gets created over here. At some point of time, you no longer have memory left. You are trying to create new object. Instead of simply saying that, sorry, that memory is used up, what the collector does is, at that point of time, it just checks if there are any objects that are no longer being used. This process is called as marking. So it tries to identify that, oh, there are some objects that are no longer being used. It marks them and then removes them. It frees up that space. Means it collected the memory. It collected the garbage and frees up the memory. But this memory is discrete, right? There are few bytes here, there are few bytes over there. Then if I want to create a memory for a large object, if I do not have consecutive memory, then it is again a problem. So what it does, the fragmented memory, it try to defragment. It try to compact it. So then again, the things are in order. Because it is doing all these things, application should not run at that time. Otherwise, it will be running into issues because of these address changes and other things. So it will wait. That's what we call a stop the world. Once this space is done, then you got again new memory or some memory left for you. So the new object actually gets allocated memory now again in the heap. If you do not have any memory left, all the objects are still being used, then you run into out of memory error when you try to create new objects in a heap that is full of used objects. So here, what we need to, if in this simple example, we have seen a heap as like one single unit, but treating this entire heap as one single unit is very much inefficient. Why it is inefficient? Because you see, you have an office, let's say you have a college campus. If the entire campus is one single unit and the cleaners comes in the morning and say like, we want to clean the entire campus, till then all of you please get out. They may take 2 hours, 3 hours to clean the entire campus. And for those 3 hours, nobody can do any work. Office staff has to be out of the office. Instead, what we do, office is having different floors, different rooms, and etc. So every time a cleaner comes, a janitor comes to a particular room, only those people, if they go out, they clean that room, but other people in other rooms, they can continue their work. That is more efficient. Means instead of having treating heap as one single unit, we need to divide it into smaller units. Those divisions are called as generations. Essentially, the heap is organized into 2 generations called young and tenured. Young generation and tenured generation. The young generation is further subdivided into Eden and survivor spaces. In the Eden space, all the new objects are created. Every time you say like create a new object, it is created in the Eden space of the young generation of the heap. Interestingly, most of the objects that you and me create and the JVM creates for internal computation purpose when it is executing, let's say string manipulations or expression resolution and etc. There are several objects gets created without we knowing it. Most of these objects are done with their job the moment you complete that function. When we say most, around 90% of the jobs, 90% of the objects are that way, lives for very, very short period of time. That means Eden space is the place where you have a lot of objects gets created and also died quickly. Then you have a minor garbage collection. During this minor garbage collection, it only looks at the Eden spaces and collects the memory from that space, means the other spaces are still there. It is not touching those spaces. It only looks at the hidden space and frees up the memory from the hidden space by identifying the dereferenced objects. And the leftover objects are whatever they are there in the hidden space, they are moved to survivor space. Means the hidden space is completely cleaned up, so that the next objects start again getting created in this hidden space. This is called as minor collection because hidden spaces are of size of very small. So they can quickly clean that room and continue with the rest of the job. So your application is not feeling that stop the world event for a longer duration. This is a very, very, very minor pass. But what happens over a period of time, your survivor space is filled up with the objects and tenured space also filled up the objects. Then there is no other go. Then full garbage collection happens. It asks the application to please stop and does the complete cleaning. Unless it does that complete cleaning, it cannot have any new memory. So let's look at that using this small visualization. So this is heap divided into young and tenured generations. Observe the color code over there. Within the young generation, again, you have two spaces, Eden and Survivor. All the new objects are created in the Eden space only. Let's say object 1 created in the Eden space. Object 2, 3, 4 also created in the Eden space, and there is no more space left. Then what happens when you try to create a new object? Garbage collector has to come into picture and does the minor collection. What do we mean by minor collection? It identifies the dereferenced objects in the Eden space. Many of the objects are statically died by that time. So let's say out of these 4, the first 3 are already died, means dereferenced. Only 4th object is left. That is moved to the survivor space, and the remaining objects are cleaned up from the Eden. That way what happened? Eden space is now completely clear. This is done very quickly, minor pass on. So this may keep on happening. So after every minor pass, leftover objects are moved to the survivor space, means those objects are surviving for a longer period of time. That way, over a period of time, the survivor may also filled in. At that point of time, garbage collector does again clean up of the survivor space. It may identify that, oh, 4th one is no longer referenced. So it is dereferenced. Only 5, 6, 7 are being still used. That means their tenure is very long. So all these objects are now shifted to the tenured region. Over a period of time, the tenured region may fill in, survivor may fill in, and Eden also may be filled in. What it can do? It has to do the complete collection, and which we call as full collection. At that time, major collection. At that time, the application, we have to wait for a little more period of time. We call that time as GC pass. GC pass, that is pass time. Application passes for certain amount of time. If this full GC is happening very frequently, very frequently, your application is stopped many times intermittently. And let's say if you are watching a movie that is written in, that application is written in Java, the video runner. If it is written in Java, and if this full GC is happening for every second, then what will happen? Your movie is stopped for every 1 second. You don't like that. So you need to write the application by keeping in mind that this is how memory works. So we need to write the application according to this architecture. Only then your application performs well. Okay, right. So here again, let's say during the full GC, it identifies that several objects across the different regions are dereferenced, and they're all removed. And then again, the story starts from the Eden space. Okay. So this garbage, as I said, the objects are marked first and then swept away next. This is called as mark and sweep algorithms. First, it marks the objects for reclamation and then reclaim the space. It may happen using different algorithms. You may have only one thread running for garbage collection, or you might be having multiple threads running for garbage collection. Single threaded collection is the one which is typically preferred in the smaller machines with less amount of memory and blah, blah, blah. And that's why this is suitable for the Dockers. Garbage collection takes a little more time, but that is sufficient for those single-threaded applications or smaller machines. If you are having a big machine with multiple cores, then you can have multiple threads running for garbage collection. Garbage collection itself happens in multiple threads. This is default in JDK 8. And then there was something called concurrent mark and sweep. In this case, not only that the several threads are doing the garbage collection, but they do concurrently, means without stopping the actual application. Means garbage collectors, the threads of the garbage collectors also running, and the threads of your application is also running. Means all the threads are running concurrent. This collection algorithm is called as CMS, or concurrent mark and sweep. This is now deprecated. It is no longer being used. Rather, it is replaced by much better collector. We call it as a G1 collector, which we'll see. No matter which algorithm we are using, our objective is to avoid that out of memory error. When there is some memory that is dereferenced, let us reclaim that space rather than simply saying that there is no memory left. So we want to avoid that out of memory error. But to reclaim that thing, we do not want to disturb the actual application. Means we want to reduce the GC pass time, or garbage collection pass time. So with these goals in mind, you keep on seeing several new garbage collectors keep coming into the picture, and that's how you got something called G1 garbage collector. G1 stands for garbage first collector. Why it is called as garbage first, we'll see. And this is the default one in JDK 11. Means as of today, most of the people in the new projects, when they develop the code, they are developing code for JDK 11, which runs the G1 garbage collector. It requires multiple processors and a very good amount of memory. And these days you are having large machines doing the job. So automatically you go with this is suitable. The interesting thing here is that it do not divide your heap into just only 3 regions or 3 spaces. Rather, it divides the entire heap into 2048 discrete regions. And some of those regions are allocated for Eden, some of them are for Survivor, some of them are for Tenure. Here they call it as old regions. And some of them are for large objects, humongous regions. How many for Eden? How many regions for Survivor? That is flexible, depending on the nature, the way application is running, depending on the way the objects are collected and recollected. The number of regions allocated for Eden, Survivor, old, and humongous regions differs throughout the runtime of the application. In the earlier collector, in the earlier garbage collection scheme that we have seen earlier, we have fixed amount of memory for Eden, fixed amount for Survivor, fixed amount for Tenure. Here it is not fixed. All right. So you'll have variable number of regions allocated for the Eden. Means at the beginning of the application, Eden may be allocated 2 regions. But when you see the way application is running, maybe few more regions are added to the Eden. That way, this is flexible. Now, how actually the garbage collection happens? The regions with the most garbage are marked globally first. That's why this is called as G1 first, garbage first. It do not look at the entire Tenure region or entire Eden region. No, it look into the entire region, but it do not collect memory from the complete Eden region. No. In the Eden, you have some regions allocated, right, out of 2048, out of which some of them are having most of the garbage. Only those things are collected first. Means it is looking at efficiency. If let's say if there is an office room with 10 rooms, 2 rooms are very much dirty, the other rooms are very much clean, then why should I keep all the rooms cleaning every time? I go to that first 2 rooms, quickly clean them so that the real work starts with all the rooms. I do not clean the remaining 8 rooms now because they are more or less clean. Right? So the cleaner is not cleaning all the rooms blindly every time. They are looking at rooms and see that if it is very dirty, only then they are clean. Means lesser disturbance to the office workers. Over a period of time, every room gets dirty. And once the cleaner finds that, oh, this is looking very dirty, then goes and cleans. That is garbage first algorithm, essentially. So during the minor collection, the surviving objects are evacuated, means from the dirty rooms, if there are any leftover objects are remaining, they're all moved to the other region, so that dirty rooms are cleaned completely in one go. So that means it compacts and reclaims the memory in one simple process, and it happens in a very short, predictable passes. Means the application do not feel the pinch. That's why these are all concurrent things. And because this is every time there is a room that is very much dirty is getting cleaned, at no point of time you find that all the rooms are dirty at any point of time. That means nowhere you will be saying like, okay, please all of you come out of the office, we want to clean all the rooms. That may not happen at all, unless you do real dirty things. So that way, full GC is very much optional. It may not even happen. Means the GC pass time is reduced. The application is not getting struck when you are using G1 garbage collector. Let's visualize that. So this is heap. It is divided into 2048 regions, even though there are not many here, but it is divided into smaller regions of equal size. Some of them are given to Eden, that is yellow. Some of these regions are given to survivor. Some of them are given to the tenured. Some of them are given to humongous, a few of them. This is like Eden spaces for the children. They make things dirty very. And survivor spaces are for middle-aged. Tenured or old spaces is for older objects, something like that. Remember, there are some regions which are still in white color, right? These things are in still white color, means these things are not allocated for any spaces, any generations. They may be allocated as and when it is required. If there are too many number of children, there may be one more room is allocated for something like that. So now, every time you create a new object, they only get created in the Eden space. So that, let's say this is yellow is Eden, right? So in this yellow Eden space, the object is created. Few more objects, they're all created in only in Eden spaces, that is yellow boxes. And you see all the yellow boxes are now filled in. At some point of time, they're all filled in. Filled in doesn't mean that they are all dirty. Some of them are some of these objects are no longer being used. Some of these objects are being used. Now the marking process happens. As part of the marking process, it does the global marking and identifies that which are of the objects are no longer being used. There are 2 no longer being used here. All the 3 are no longer being used. 2 more here, 2 more here, 1 only here, 1 only here, all the 3 here, and all the 3 here. So which rooms are very much dirty? This one and this one. This is completely dirty. There are no useful objects here. Here, majority of them are dirty. This one and this one, of course, sorry, and this one also. This one as well. Whereas these 2 are having less amount of dirt. So what will happen now as part of sweeping? Only the regions which are having most of the dirty objects are cleaned up. Means these are all identified. So this region is mostly dirty. This region or Eden is mostly dirty. This Eden is also mostly dirty. But these 2 are not they are dirty, but not very much. So they do not touch this. They touch only 1, 2, 3, 4, 5, 6 regions and clean them. Those dereferenced objects are cleaned. So there are some leftover objects here. They are all moved to a new region, that is survivor region. Now what happened? 1, 2, 3, 4, 5, 6 Eden spaces are now completely freed up. They are now available again for object allocation. So this is how things are done again and again and again. So because you are having some more regions allocated for meant for or ready for Eden or survivor as and when they are needed, most likely, unless your application is written in a very bad manner, most likely you never see that all the regions are filled in with all the work, all the data objects. Means you never see that need for doing the full GC. Means your application runs smoothly. This is how the garbage collection works in the case of JDK or JVM level. Right? So that's it. This is the architecture of the JVM. So in summary, Java Platforms offers you platform independence because of that interpreter. but also it gives you performance because of the adaptive compilers. Java platform, like any other platform, handles both process management and memory management. Sorry, there is a typo here. Process and memory management. All right. So as an application developer, if you know how this process management and memory management take place, just like what we have seen, now you know, like, oh, I need to write the application in certain manner. I'll be having another session when we actually deliver this as a TechChat session as part of Sversity program at campuses. We also talk about what are the things that we need to do to write the performant applications. Like as a developer, now we know how these things work, what it means to the developer, what are the best practices that we need to follow when we write our Java applications so that they are efficient and performant. Right, so that's it. We are done with this session. Thank you very much. We'll meet you in the tech chat.